All right, I wanted to talk about your most recent quiz a little bit. Um, so, because I mean, you've done worse on quizzes than on this one, but it's not that it's not that you did terribly, but I just wanted to clarify some things that I think are some at this point pretty common sort of misunderstandings. So for the first question on the quiz, we were looking at this sequence here. -1 to the n plus 1 over n squared from n equals 1 to infinity. And every single one of you were able to write out the first 5 terms without any difficulties. So you did well with that part. The issue came when you were trying to find whether the sequence converged or diverged. And then, if it did converge, then what its limit was. So, several of you did this. You just said, like, well, limit as n approaches infinity of -1 to the n plus 1 over n squared equals 0. And you just, without really giving any justification for it. And to be clear, we'll see stuff like this pop up a lot, and so I don't expect you to justify this every single time, but like the first time you see it, you definitely need to justify it, right? And this is the first time we've seen this kind of thing, because I want you to appreciate I want you to appreciate this. So some of you tried to show a little bit more work, and so you maybe wrote down something like this, but this is still wrong. I mean, as n goes to infinity, n squared is definitely going to go to infinity, and 1 over infinity is, of course, 0. But the issue is this part up here, right? It's like, what happens with this alternating part? It's not true. It's not true that -1 to the n plus 1 goes to 1 as n goes to infinity. As n goes to infinity, -1 to the n plus 1, well, if n is a whole number, right? If n is a whole number, then the best you could say is that this thing is going to alternate between -1 and +1. So it's not like a fixed value. It jumps between -1 and +1. And actually, a couple of you made that observation, and you said, therefore, it diverges. But that's also not correct, because this thing is alternating between -1 and +1, but the denominator is getting just huge, and so the numerator is sort of negligible at that point, and so it is going to 0. But this is not the way to show it. This is not the way to show that it goes to 0. You can't just say that -1 to the n plus 1 is going to go to 1 as n goes to infinity. And anyway, this is assuming that n is a whole number, right? Imagine if n is not a whole number. Imagine that n is like 1/2, for example. Then you have -1 to the 1/2 plus 1. So -1 to the 3/2, right? So that means you're going to be taking the square root of -1 at some point. So you're not even going to get a real number. So as n gets really, really large, -1 to the n plus 1, sometimes it's not even a real number, right? So it definitely requires some justification, right, to say that this thing goes to 0, because, I mean, for some values of n, it's not even real. So like I say, it takes some justification to say that this thing goes to 0. Now, fortunately, there are a couple of tools that could come in handy. So I'll show you a couple ways that you could show that this thing goes to 0. So one way, and this is what I put in the solutions to the quiz that you can look at if you're interested, but one way to show it is to use theorem 9.1.6, right, which says that if the absolute value of a sequence goes to 0, then the sequence goes to 0. And so the way that would look in our case is, if we were looking at limit as n approaches positive infinity of the absolute value of -1 to the n plus 1 over n squared. Well, then you could say, all right, well, so the absolute value here is going to be always a positive 1, right, over n squared. And then this, as n goes to infinity, is very, very obviously just 0, right? Because the denominator is going to explode, the numerator is going to stay this fixed value at positive 1. So since the absolute value goes to 0, the original sequence goes to 0. So you could say, thus, absolute value of negative 1 to the n plus 1 over n squared goes to 0, and therefore by theorem 9.1.6, the original sequence without the absolute values goes to 0. All right, so there's one way that you could show that it converges to 0. Another tool that you could use to do the same thing, and we also went over this one in the notes. So we went over 9.1.6, but we also went over theorem 9.1.4. And a couple of you did this, and so a couple of you did use this theorem. I don't think anybody actually stated the theorem. That's okay though. I mean, like I understood that it was that this was the theorem you were using. So several of you did use this and do it correctly. But a couple of you used this, and I didn't expect it, but it's totally correct, right? So what this theorem says is that if the even-numbered terms and the odd-numbered terms both converge to the same limit, then the overall sequence converges to that limit. So I'm not going to rewrite the whole thing, right? But here's what the theorem says, right? A sequence converges to L if and only if the sequences of even-numbered terms and odd-numbered terms both converge to L. And then we looked at a couple examples where we didn't have any alternating signs going on here, but we did have this thing where like 1/2, 1/4, 1/8 is going to 0, 1/3, 1/9, 1/27 is going to 0, and therefore the whole sequence is going to 0, right? Whereas here we have 1/2, 1/3, 1/4 is going to 0, but 1, 1, 1 goes to 1, and since they're approaching different things, the sequence diverges, right? Anyway, so the reason this theorem is useful here is because you notice that when you write out the first several terms, you get what? -1, or no, it's actually +1, right? -1/4, and then 1/9, and then -1/16, and so forth. 1/25, and etc. So if you just look at the odd numbered terms, it's 1, 1/9, 1/25, and so forth. That's going to go to 0. And then if you look at the even numbered terms, it's -1/4, -1/16, -1/36. Those are going to go to 0. And so by theorem 9.1.4, you can say, since the odd numbered terms go to 0 and the even numbered terms go to 0, the sequence goes to 0, right? So that's another approach you could have taken to show that this limit is in fact 0, right? So that was the first problem on the quiz. And then the other one that I wanted to talk about, the second problem, obviously, the only other problem on the quiz, but you were supposed to show that this sequence here, n over n squared plus 10, is eventually strictly decreasing. And there were 3 tools that we talked about in the notes that you could use. So one thing would be to look at, one way that you could do it would be to look at the difference of consecutive terms. Okay, and this is where you would look at a sub n plus 1 minus a sub n, right? So you say a n plus 1 minus a n is n plus 1 over n plus 1 squared plus 10 minus n over n squared plus 10. And then your goal is to show that for some value of n and every value thereafter, this thing is always negative. Because if it is, then you know that the sequence is decreasing, right? Anyway, that takes a little bit of work, right? It's like you've got to say, goodness gracious, I mean, you've got to get common denominators, so you've got to say n plus 1 times n squared plus 10 over here. I can expand that, I suppose, call it n squared plus 2n plus 1, but then I add 10 and get 11. All right. Oh, but I've got to multiply by n squared plus 10, right? Okay, and then minus n times this thing, n squared plus 2n plus 11 over n squared plus 2n plus 11 times n squared plus 10. Okay, then you can like distribute, you can cancel some stuff. I guess we should do it, because I've got to show you where some of you kind of went wrong here. So expanding this, I would get what? N cubed, and then n squared, and then 10n, and then 10. Okay, and then minus n cubed, minus 2n squared, minus 11n over this monstrosity of a denominator, n squared plus 2n plus 11 times n squared plus 10. Okay. So anyway, the n cubes cancel. You've got a negative n squared. 10n minus 11n is a negative n. So those are gone. And then plus 10. Okay. Okay. So now one thing that did dismay me is that some of you did some crazy crap, man. Some of you were like, oh, we can cancel that. No, we can cancel that. And no, you can't. Are you serious? Is this like 8th grade algebra class? No, you can't cancel like terms. You can cancel common factors, but that means you have to be able to factor something out. You have to be able to factor out the same thing from the numerator that you can factor out from the denominator and rewrite it as products, right? And then you can cancel stuff out. But you can't just cancel out common terms like that. Come on. No, that's not how that works. Anyway, but the point is, when you get down to this step, you have to show that this thing is less than 0 for some, in this case, it's for n bigger than or equal to 3, right? But this is not something that you can just conclude, right? You have to show this, and several of you wrote out several terms. It's like you wrote out the first like 5 or 6 terms of this sequence, and then you said, oh, see, so after 3 it's a decreasing sequence, but that's not a proof, right? Maybe it turns around. Maybe after like the 300th term, it starts to increase again, right? You don't know. The only way you could know that is if you actually algebraically prove that this is the case. And man, you've got your work cut out for you there. The way that you would have to prove this is you would have to first of all, you'd have to make like a sign chart. So you'd have to solve for when the numerator, the thing is, you're interested in knowing when this thing changes sign, right? So you'd have to solve for when the numerator changes sign, you'd have to solve for when the denominator changes sign, and then you'd have to make a little number line with all of the places where the thing changes sign, and make a little sign chart to figure out where the thing is positive and where it's negative, right? And then you could say, oh, well, so it's less than 0 on this region and on this region, and then it's bigger than 0 here, here, and here, or whatever, right? Whatever the case is. That's a lot of work, and I'm not going to go through all the nitty-gritty details, but you'd have to actually show it algebraically this way. So personally, I wouldn't use this method on this particular problem. I wouldn't do a difference of terms here. But this is what you'd have to do. You can't just say that, like, oh, because it's decreasing for like terms 3, 4, and 5, therefore it's decreasing for every term after that. It's like, you don't know that. You don't know that, and you didn't prove that, right? Just by writing out the first few terms. You actually have to show it algebraically. which you have not done here, right? You haven't done that. So you'd have to do all of this work. Man, that would be a nasty, horrible monster of a problem. So I'm not going to finish it, but yeah, that's how you do that one. The second tool that we said you could use to show that something is, eventually monotone is to look at the ratio of successive terms. So you could look at a ratio of terms, right? This is where we look at a sub n plus 1 over a sub n. And in order for this thing to be decreasing, we need for this to be less than 1. Okay? In order for it to be strictly decreasing, we need for this ratio to be less than 1. Okay, this I think is a little bit more promising than the difference of terms, in the sense that I think it's a little bit less work, but we'll see. All right, so you would get n plus 1 over n plus 1 squared plus 10 times n squared plus 10 over n. Oh man, and this is where people really went crazy with the crazy cancellations that don't work. But yeah, okay, so we'd have, n plus 1 times n squared plus 10 over, we already did this, right? This was n squared plus 2n plus 11 times n. Okay, and yeah, again, people did some crazy stuff where they're just like, oh, boom, boom, right? Not how it works, guys. Not how it works. Not even close to how it works. You can't cancel like terms. You can only cancel common factors. And I think you're kind of hard-pressed in this particular example to find any. But anyway, so you've got to somehow show that this thing is less than 1. And actually, I think I lied a second ago when I said I think this is maybe a little bit less work. I think, if anything, this is probably more work. Because to show that this is less than 1 for all n, you have to move this 1 over to the other side, get common denominators, rewrite it as a single expression, and then do the same thing that you had to do here. At least that's one way that you could show it. I wonder if there's another way you could show it. Yeah, I mean, I don't know. But again, it's like several of you got to this stage and you were like, oh, well, I'll just write out the first 5 or 6 terms and then show that, after the third term they're all less than 1, and so that'll be good enough. But again, that's not a proof, right? Because you don't know that it won't turn around after the 7,000th term. You don't know if it doesn't turn around at that point. The only way you can really know that is to actually do the algebra here and show that doesn't happen. So again, I wouldn't use this method either. The method that I did use is the third one that we talked about, which was to take derivatives. Right? And basically what you do is you just treat this sequence like a function, right? So you say f of x is x over x squared plus 10. And then you can say, all right, so then f prime of x is low d high minus high d low over low squared. And then just like in the first case, your goal is to show that this thing is less than 0, because if the derivative is less than 0, then the original function is decreasing, right? So you want to show that this thing is less than 0. And so we can say, all right, so f prime of x. This is what I actually did on my solutions. But we can say, okay, so f prime of x is going to be x squared minus 2x squared. So it's going to be a negative x squared plus 10 divided by x squared plus 10 squared. And to figure out when this thing is negative and when it's positive, I mean, you have to set it equal to 0 and solve, right? So you have to say, all right, so So maybe I'll say negative x squared plus 10 over x squared plus 10 squared equals 0 if and only if x squared plus 10 equals 0. Sorry, negative x squared plus 10 equals 0. And that happens if and only if x is plus or minus square root of 10. And then you have to make a sign chart, right? You can say, okay, so those are some critical values. So I can plug them into the derivative to see which one makes the derivative negative, which one makes it positive and stuff, right? Is it right? So you do a little test point thing. Anyway, by the way, square root of 10 is approximately 3.16. So if you plug in like, so obviously in the context of looking at a sequence where n is bigger than or equal to 1, you don't really care about the negative solution, right? You really only care that, okay, so this function changes sign, at 3.16-ish, right, at the square root of 10. So if you plug something in less than the square root of 10, like 3, and something bigger than the square root of 10, like 4, then you see that, like, so f prime of 3, for example, would be negative 9 plus 10, so that's a positive 1 over something positive. So it's going to be positive. And f prime of 4 is going to be a negative 16 plus 10, so that's going to be a negative over a positive, and so it's going to be negative, right? And since square root of 10 is the only place where the derivative changes sign, you know that the derivative is going to be negative for any value of x bigger than 3.16, right? So f prime of x is less than 0 for all x bigger than or equal to, or I'll just say strictly bigger than, strictly bigger than square root of 10. So what does that have to do with your sequence? Well, so that means definitely for n bigger than 3.16. So for n bigger than 4, this thing is decreasing. But if you actually look at the terms, and I state this on the quiz, right? So if you actually look at the terms, they go like this. And so actually after the third term, things start to decrease. But this is the justification that lets you know that that's never going to turn around, okay? It's never going to start to increase again, because in order to increase, the derivative would have to change sign, and it doesn't, because you know the only place the derivative changes sign is at square root of 10, okay? So anyway, so that's that one. Again, like, you have to show these things. You can't just write out a couple terms and say, oh yeah, it looks like it's always negative, but you didn't prove that. You just looked at a couple specific examples, right? You need to prove it generally, and this is how you would do it. Now, it's not that it's impossible to do it using one of the first two methods, but man, that's a lot of work. So anyway, so that's that.